Hey Rob, I have this problem. I took all these great pictures and I want to put them on my website, but they need to be in widescreen format, and if I crop them or stretch them, they just look terrible. What can I do?
You know, I've had that problem, and there's a solution.
There
It's called
is?
seam carving.
What?
Josh, it's really simple.
That sounds so hard.
No. It's not hard, alright?
Really?
You're just gonna get an energy image, alright?
Okay.
You're gonna use a Laplacian.
Oh.
Yeah.
That doesn't sound so bad.
And then you're just gonna go down, and you're gonna start at a pixel, and then you're gonna look at the 3 pixels below it.
Okay.
And then you're gonna pick the lowest one. And then you add those two together, and you just keep going. You create these seams that carve through the image.
Oh.
And then it
doesn't matter that you take them out, because they don't affect the image that much.
Exactly, because of the energy.
Oh, and you could put them in too.
Well, yeah, maybe.
We'll see. For those of you who can't understand this in 10 minutes, let's consider a pixel and its 3 neighboring pixels below.
So here the pixel in question is the digital count 38, and we're going to look at these 3 pixels below it and find the lowest one, which is obviously there on the right, 23. Since 23 is the lowest pixel, if we were tracing a seam, we would move from 38 to 23. To find seams, we create a seam map which contains the running sum of each seam in the image as we move down through it. So, for this pixel, for the pixel 38, the value in the seam map would be equal to 38 plus 23. Now let's take a look at an example seam map.
If we were using this image, an example of the vertical seam map would look like this. So the running sum of the seams in this seam map is higher in areas of the image with high energy, as you can see, like the waterfall, whereas relatively constant regions, like the water, don't have such high energy.
The ideal seam to be removed would be that with the lowest energy. So you want to search along the bottom row of pixels to find the lowest value, and then trace that seam back up and remove it.
In our implementation, we also calculated a horizontal seam map for removing horizontal seams. The same code was used, we simply passed in the transpose of the original image. Oh, that was the longest 10 minutes of coding of my life. Think this looks right?
Yeah, how did you do that so fast?
It just made sense.
Here we have an example where 25 rows and 25 columns were removed, and as you can see, the seams carved through the image and did not affect image content.
As you can see, seams are being removed first vertically from the image. For the sake of example, removing the maximum energy seams from the image greatly distorts important features like the waterfall.
The first problem, which can easily be seen in this example, is that every seam originates from a corner.
This is a problem because the truly optimum seam path is not being followed, so important image features are being distorted.
Here's an example from the original paper in which you can see that seams should not always originate from the corners.
In the examples we've shown, the seams have been removed first vertically and then horizontally. For most images, this is not the optimum removal order.
The authors of the paper decided which rows or columns to remove by implementing a transport map.
The transport map is built by looking at the seam map and picking which seam is minimal, either a horizontal seam or a vertical seam.
So the transport map is created by following a path through the image of removing seams in the horizontal and vertical directions until the entire image is gone. And then in order to find the optimal order to remove seams, you will then follow the lowest path through this until you have removed enough columns